So what are subspaces? As the name suggests, it is a subset of a vector space, like a small portion of a bigger universe. There are only three main properties you must keep in mind. A subspace must have the zero vector, a subspace must be closed under addition, and a subspace must be closed under scalar multiplication. If you remember, these are basically the same as a vector space. So what do you think the subspaces of R3 would be? Is a plane and a line a subspace? The answer is no. A plane passing through the origin and a line passing through the origin are the subspaces for R3, but why is there an emphasis on having this zero vector? Why must the plane and the line pass through the origin? Let's understand this by an example. Suppose we have this line that doesn't pass through the origin. Let's take two vectors on this line. When I add the two, the resultant vector lies outside this line. This means that the closure and the addition property is violated. The sum of the two vectors should have been inside this subspace as well. Now let's look at if I had a line passing through the origin. I take these two vectors and add them up, and the result still stays on the line. Hence, the line passing through the origin is a subspace. As an exercise, try and imagine the same example, but with planes. So let's look at this statement here. If U1 and U2 are subspaces of V, then U1 union U2 is a subspace as well. Do you think this is true? The answer is no, this isn't true. Pause and think about it for a second and see if you can find the logic behind it. Let's say U1 is the x-axis and U2 is the y-axis. They are subspaces of V. Now, their union is all the points on x-axis and all the points that lie on the y-axis. Since we want to see if their union is a subspace, this means it must be closed under addition, right? So let's take 2 points, x0 and 0y. On adding them, we get xy. However, this lies outside the space of U1 union U2. Thus, this isn't a subspace. Do you think this is a subspace? 2x minus 3y is 0. Well, we know this is a line. But does this pass through the origin? In other words, does it contain the zero vector? Let's substitute 0 for x and y. We do get 0. This means this is a subspace. What about this one? 2x minus 3y plus z equals 5. We can see that this is an equation of a plane, and it doesn't contain the zero vector, as we have a constant term that ruins the game. It gives 0 equals 5, which isn't true. Thus, this isn't a subspace. The next thing related to subspaces is the dimension. The dimension is the number of vectors in the basis. Keep in mind, this is not the number of components that make up a vector. Suppose we are given this, and we are asked to find the dimension of this subspace of R4. For such questions, we always try to split the vector into multiple ones. To do so, we first pick one variable and put all others as 0, and then select the second one and put all others as 0, and so on. Okay, so let's actually do it and see what we get. I'll first put B as 0. This gives me A, 3A, A, and 0. Now we put A as 0. This gives me minus 2b, 0, b, b. Now we can just factor out a and b and get this. You can verify that this gives us the original vector we began with. So these two new vectors are my basis vectors. A and b just signify that when we give them different values, we get a new set of bases. But the number of vectors in this basis always remains 2. Therefore, the dimension is 2. Let's look at one more example. It says find the spanning set for the plane x plus 2y minus 3z is 0. So what's a spanning set? A set of vectors that spans a space? Well, that is nothing but the basis, right? So we need to find the basis for this plane. We can write this as x 2y minus 3z. But hey, if you look closely, we can write x as 3z minus 2y. So now I'll put y as it is and z as 0. This gives me minus 2y, 0. Now I'll put y as 0. This gives 3z, 0, minus 3z. And now factor the 2 out and we get this. So these are the basis vectors with dimension being 2 because the number of vectors in this basis is 2. Notice how we can have infinite bases just for the same plane. And we just have to choose different values for y and z here. We've barely scratched the surface of subspaces and dimensions. There's a lot more to come. We'll be diving deeper into them in the future videos. If you found this video helpful, leave a like and subscribe for more linear algebra content.